Well, okay. I guess some people are joining now. I guess we can start, Reda. So I'm very pleased to introduce Reda Chhaibi. He's a member of the Institut de Mathématiques de Toulouse, and he's also an associate chair in Fabrice Gomboa's chair in INIT. He's been working on free probabilities, and he's going to talk to us about this today. We're all very eager to learn about this new approach. The title is Free Probability Theory and Newton Lilypads, or Lippypads, sorry, Lippypads.
Lilypads, yes, that's a typo.
It should be Lilypads, that's what I thought. Lilypads as a solution to the wasteful tuning of neural networks. Thanks a lot, Reda, for coming to talk to us about this.
So thank you very much, Nicolas, for the introduction. So Fabrice apologizes for not being here because he went to get his COVID jab, like the third dose, really far away from Toulouse.
He should do that. That's good.
So so today I will tell you about the joint work with Tariq Dauda, who's actually a childhood friend who did his PhD in the US in Quebec in machine learning, and Ezekiel Khan, who's a PhD student at the Ecole des Ponts. So actually, this work is a bit of an adventure with actually much more math than we expected, and actually, so you'll see. So I think this is a nice coming together of theoretical things and machine learning things. So first, let's start with the introduction. So my first points will be, okay, first, why is the tuning of neural networks wasteful in time, in resources, in money, in brain power? And then I'll recall the basic model of what is happening, and then thanks to this, so the plan is, first I'll start with the empirical results as quickly as possible. So therefore for part one and part two, I think this is very friendly to anyone who's interested in neural networks, in machine learning, who has a little bit of practice, just a little bit. So part 3 and 4 will be about the theoretical stuff and the numerics. So let's start. So let's start by some clickbait statements. So the first one is, okay, so this slide is aimed at convincing you that the tuning of neural networks can be very wasteful. So I found a paper by Strobel and Al, so that basically computes the carbon footprint of training BERT, so which is a pretty well-known neural network, and running it even on state-of-the-art a GPU is comparable to that of a trans-American flight. So it consumes quite a lot of energy. And actually, this is for one neural network where you have chosen all the hyperparameters and where you're happy with everything. So suppose now it's you do even worse than that. It's you're trying to do hyperparameter optimization. Try different size of layers, different initializations, different non-linearities, and then train all of them and then pick the best one. So this is basically, yes, the most, the simplest way of doing it. And so here, actually, here's, yes, but this is a funny, so this is a funny diagram where you can see the comparison. So training BERT on, the basic one on GPU. So in terms of LBS, I guess this is pounds in CO2 of emissions of CO2. So that's the number. So air travel, New York, San Francisco. So it's a little bit comparable. If you're a human, on average, during 1 year, so this is what you will consume. This is what you will breathe. And this is the CO2 footprint of a car. So as you see, this is much bigger. It's and then if you want to do this very big hyperparameter optimization of very big transformers. We're training lots of them, so it's basically it's worse than this one, but you did so many times that, as you see, so it's a little ridiculous. So as I said, these are rather clickbait statements, because this deserves to be moderated, because this is for training. Because once you're happy with one architecture, so this is the training part, and you tend to just use the same one for inference, yes, like, which is much less costly. But okay, so this is like the easy thing to say. But on the other hand, you could yeah, I mean, but for me, it's like what really matters is that, so I feel that, you know, this is a lot of waste of brain power. Like, you're trying things, you know, and you feel that, yeah, so this whole procedure is very like wasteful in researchers' time and data scientists' time. You know, perhaps you would rather be with your kids or having a drink with friends. So let's try to see how like we could maybe try to be less wasteful. So like before getting into the like mathematics and the theory of it. So and for this, I will just adopt a very simple setup. So I will consider just a feed forward network with fully connected layers, and this is the usual drawing. So on your data set, you get x1, x2, x3, etc. So let's say they're images, and the very simple case, if they're images of MNIST. So MNIST are pictures of 28 pixels by 28. So your initial value is in the 28 square, which is 784, if I remember. Then you propagate this with the weights that you're training until the final layer. So if it's MNIST, so here it's like you should be in R10 because then you have 10 classes. Or if you're trying to make some sort of auto encoders, like for example, it's again of the same order. Okay, so what are the hyperparameters of this problem? So it's just the vector of widths. So just like the size of, so this one is fixed, but this one is like you can pick whatever you want, this one, etc. So this is the ends. Big ends will always be the vector of widths, and the bold font N like will denote like the vector of all the sizes. You can also think of the non-linearities as part of the hyperparameters, because like your so in a typical neural network fashion, so you have weights and then biases, and what you do, so you do from a layer to the next. So you do the usual affine transformation, make a non-linearity, and the non-linearity, of course, here is pointwise. And then you go on like with this business, okay? So that's the typical framework, and it's okay. And perhaps this is too simple, but as you'll see, so the take I will have on this is pretty theoretical, and the goal like will be to prove that it serves a purpose. And later, like for the conclusions, like we'll mention maybe different things where you have convolutions, or like where you do something that is perhaps like more aligned like with what people do in practice. So first, okay, so before asking the question of what is the best hyperparameters, so let's see what happens. So of course, like when you compute, like you front propagate, and then like when you back propagate for the differentiation, so it's like you're computing Jacobians, and the Jacobian computing during back propagation, so can be written explicitly thanks to the chain rule. So so I like this notation for the chain rule. You just differentiate like a physicist, and you just write this as a product of matrices. And so actually here, maybe it's a good idea to give you the to remind you of the previous expression. So here, maybe I should pick this guy up. Okay, so if you use this and you differentiate, so you realize just because of the chain rule, so you're differentiating the nonlinearity pointwise. So this gives you a diagonal. So the diagonal Jacobians, then you differentiate like this guy, like with respect to the XL minus one. So you get like the weight matrix. So actually the Jacobian has this alternating structure, which is pretty explicit with the weights times something which is diagonal, and the diagonals like matrices is just the non-linearity prime and times the pre-activations, like which is like this guy. Okay, so let's discuss. Okay, so yes, like what happens. So during gradient descent. So technically, if you're doing machine learning, so you do some sort of gradient descent. So you have many of them, but I'll just take like the basic gradient descent thing, and the training is actually. So excuse me, I will just. I'm trying to make sure that you guys see like what I'm writing. Okay, so that seems okay. So my parameters, like which are all my weights and biases. So this is the arg min of a loss, L theta, and actually, so theta is actually like all the vectors of. So it's like this is all the entries of weights and biases, with L being 0, 1, 2, until L. Okay. So let's pick a typical case, because of course people like love doing like very different things, and it's relevant. So you have many possible losses. So let's just say I'll pick some sort of D, which is a distance between the output of my neural network and the yi, like which is either a label or the same thing if I am in the case of an auto encoder. So D is a real value distance or a similarity function. The xi's are the inputs of the input vectors, and the yi's are the sought after are the sought after output vectors. Okay, and you do like your gradient slide descent like happily, where alpha is a learning rate, and you're like, okay, so first thing first. So let's say, okay, so what happens? So if I look at the chain rule and look at it, so actually it's the same computation as before, because here I just have to look at so actually I do the same chain rule as before. And I find that I have a matrix of the same 4 as before, so like with these alternating product that is sandwiched between two things that are actually quite simple. So the first one here, so actually select this one, I'm sorry, so this one is not here, but you'll see it's relevant. So you have, so it's sandwiched between this first derivative. So I differentiate like with respect to the first coordinate of the distance. So this is a pretty simple thing. And this thing as well. So I realized that the ugly person in the middle is this one. Okay. And so first intuition is that, okay, so this is a sum. Generally things are IID taken within the data set. So just because of a CLT and law of large numbers, so this thing looks like a Gaussian. So I have my ugly guy sandwiched between actually something that looks like a Gaussian vector and this guy, which is actually computable. Okay. So okay. So therefore, actually, I need like to focus on this. So just because of transformations of Gaussian, sorry, so I'll just go back here. So just because of the transformation of Gaussian vectors, I have this matrix here, and I'm transforming my Gaussians like vector, and here I'm forgetting about this. And so therefore, actually, this guy times its transpose, or so this gives me the correlation function I mean, it's like the covariance matrix of the gradient step, right? So once you realize this, so you're like, okay, so I'll have to look at JNs, Jacobians, like which are, this is a pretty big matrix. And this thing is a large product. So let's just fix the ideas. So a large product. So large products. So this is the number of layers. So for me, this is, I mean, in the neural networks like this, like that I've been playing with, it's from 10 to 100. So perhaps for some of you, so that this is not big enough, but you know, this doesn't, it's not really like important. And the matrices, there are, I mean, even in the simplest cases of MNIST, CIFAR, even basic, very simple like data sets, its size approximately 1,000 to I mean, so of at least 1,000. So I guess like this is good. So okay, so since basically at the beginning, if you have no information, like your neurals, like networks, like is lost, there's no structure. So you realize that the best thing to say is that, okay, like you have a Gaussian vector of a loss, of the differential of a loss, multiplied by this matrix. And if it's, and this matrix like basically gives the correlation structure of the, like the covariance like structure of the gradient step. So if many singular values are small, you have gradient vanishing. So basically here, this means you have a freeze. Like your training is not happening, it's just completely blocked. If you have gradients like explosion, everything is unstable and you have numerical noise. So actually it's like what we will do here, like the goals. So this can be more like justified, but this is part of the previous literature by Gloro Bengio, by yes, actually by all the papers, yes, like that's like this foundational paper of Gloro and Bengio. Which explicitly say that basically, okay, it's like you should look at the spectrum of this thing. You should look at this spectrum of singular values, and okay, and you should avoid gradient vanishing and gradient explosion. It's like with this basic intuition. And the goals of this talk is actually try to understand like the spectrum as a function of the architecture, basically large N's. And varying initializations of the weight of like matrices, because we're interested like in the beginning, and you know the learning process is very affected by what is happening at the beginning. We will give an effective computation recipe, and all of this will be very. So this actually is completely theoretical. You could say, okay, like you're computing things, you're doing things that seem perhaps removed from reality. And here we'll do something that is very empirical and show you that the indicator actually means something. And so are there any questions? So do you want me to actually pick questions as I'm going, or maybe at the end? So I'm not really familiar with how you want to proceed.
Oh, Reda, it's really as you wish. But you know, let's see. We can, if there are any questions of just clarification, we could take them now on this intro part.
Yeah, sure. So please, everyone, if you have any questions so far, please just go ahead. If not, I'll just continue. So like, so I like it's like interactive talk. So you can interrupt me whenever you want. Okay.
I just want to ask: the N is the size of the number of depth, the number of layers, or what it is?
Oh, so you're asking me about the size of the number of, okay. So actually, so I'll give you a theory. I'll give you asymptotic answers for N large. So then you will ask me, okay, starting for which N is it correct? So is it like 1,000, 2,000? The answer is, so I'll make this comment a little later because like the tool I'll be like using, which we call free probability. So I'll tell you exactly for which regimes, so like this is correct. And 1,000 here is enough, basically.
Okay, so N is the size of each layer, right?
Yes.
Okay, wait, okay, thank you.
Maybe one comment or question, it's Pierre Weiss.
Sure.
Here, your Jacobian, you would like to control it uniformly over the gradient descent trajectory?
Not really.
Du coup, pour générer une nonne, etc.
Somebody turn off your mic. Somebody's discussing. Please. Go ahead,
Okay.
Reda. Yeah.
So regarding yes, like the question of Pierre Weiss, actually it's like you'll be disappointed. I don't want to so I don't want to control it along the entire learning process, and I can't actually. It's like everything I will tell you will be mainly true at the beginning. I know theoretically it is true at the beginning, and so far it's like we don't know. It's like the story that I will tell you today, during how long this free probability regime will be true. So think of it as something at the beginning. So the question I'm basically asking is, at the beginning of the learning process, is my neural network pretty stable, nice, and does it have a chance of having a good start? This is basically the question.
Thank you.
So okay, so then I'll give the empirical results like before the math. So I hope like this will convince you at least that like the theory afterwards will be useful, and hopefully it's like this will give you the patience of listening to it. So it's like what is done now. So today is like nowadays, like so this is a. I mean, it's like this will be a caricature, so of course, but just bear with me. So this is a caricature of, it's like what okay, so if you're a data scientist or you with the neural networks, and here you recognize that I prefer PyTorch. So like you start with a more or less, so you start by working on a data set, you try to clean it. Once you're happy and relatively clean, you design a neural network. So basically it's like this is the grind part. Maybe it's like you could say like this is like the artistic part, and then comes a phase that that actually I found a little like not so a little problematic. So you pick just layer sizes, you pick non-linearities. Actually, it's like if you ask PyTorch to just launch the training, it does randomly as the initialized weights, and the default initialization is one of them. You have other of them, and so this is a screenshot from the documentation of PyTorch called like this is the Xavier normal initialization, and it initializes all the weights according to the methods that is described in Understanding the Difficulty of Training Deep Feed-Forward Neural Networks by Gloro and Benjo. And here it's normal distribution. You can also do uniform. There are also so many variants. And the idea is, okay, so you have this factor and you have this gain. So the gain generally is picked at 1, but you can customize it. You can put 2, 3, whatever you want. But this factor actually is very smart. Actually, so this factor square root of 2 divided, okay, so the square root of 2 actually is not like that smart, but the normalization here is, so the fan in is just like the size of, you have a layer, you have the incoming size and the going out size. So that's the fan in and fan out.
You mean the arrows that are the links that are coming in and coming out, right?
Exactly. So that formula is actually very smart, because actually from the point of view of stabilizing the spectral measures, if everything is of size n, the free probabilities theory that I will tell you afterwards. So this is not a consideration it's in that paper, but nowadays it's pretty well understood that if you renormalize weights by 1 over square root of n, which is more or less this, if everything is equal, so 1 over square root of n is basically like this factor, then spectral measures will converge. So, and I find this pretty amazing because so the order is correct. And then you had other papers you have other methods, K-mean and other things, where people discuss the square root of 2, and some people advocate for 3 or whatever. But the method we will propose is more global. Basically, what we will say is that this constant, it should better be picked up depending on the entire infrastructure. the entire architecture. So okay, but that's what's like what people do now. It's like as a standard way in every machine learning framework. So you just randomly initialize, launch the stochastic gradients, let descend, and hope for the best. Oh, so so which part is more the most important? Hoping for the best or doing the rest? I mean, maybe it's like picking the stochastic gradients let descend. So here in ANIT, all the specialties are present, and people is like to focus on different parts. But this is like a caricature of what is happening. So, and the part that I have a problem with is this one. So hope for the best, and if it's not the best, then you repeat ad nauseum. So you just repeat and you repeat and you repeat until it's like you get something better. And I found like this procedure extremely daunting and wasteful in time and resources. And the beginning, it's like in terms of carbon footprint. So you saw it's like this part as actually is the terrible one. So you're like, maybe I should have known since the beginning. What should I have done in these phases? Maybe.
Yeah, Reda, can I just a comment. Just seems like this part is like black magic, and you throw some things into the cauldron.
Yes.
So it's also not very nice scientifically because we don't really know what we're doing when
exactly.
Okay.
So here I'm not pretending that I will give you an explanation of the black magic. But so let's hope, yes, that I'll give you a little framework to begin how to think about it. Because, okay, so actually, my framework, as you saw, is pretty constrained, but with this fully connected feed forward. So here, I'm rather restricted here, but I'm pretty happy it's like with the answer I'll present you. So there, I hope to show to you that actually here's something that actually tells you. Okay, so let's describe an experiment that actually like you can do at home, and which is actually very simple. So we first did something pretty complicated. So we had, okay, so first, so the thing I want to tell you today is some sort of indicator of stability and performance of the hyperparameters. So if you have an indicator, any indicators, yes, so you can cook up one. Maybe it's so you have an indicator, and then it's like you want to test it. So the testing procedure is pretty simple. So you just take some standard like neural net. So here's I picked an MLP, a multi-layer perceptron on a standard like data set, say MNIST, CIFAR, anything. And then we do a random hyperparameter search. So I pick, so I fix L, and then I pick like different layer sizes. So I could pick different L's as well, actually. And then I pick like different gains at initialization. And then for every one of them, I have some architecture. Once I have this architecture, so I can compute and record like theoretical indicators. For me, like this will be FPT being free probability theory. We will say later like what is this, but I chose to tell you, okay, this is my own black magic. I mean, actually, so it is not mine. So it is like the black magic of, so I'll give you the names later. And here, and these FPTs like indicators, in fact, they are quantiles of the spectral measure of the Jacobian. So that Jacobian I showed you, like the theoretical one with the model, I can actually compute that thing as a measure, as a spectral measure. And these are just like the quantiles, and I'll use these as indicators. So here and in our work, so we presented some algorithm that we're pretty happy with, that works pretty quickly. So that computes like this density, 100 points, 200 points, 400. So here, here in time, in milliseconds. And once it's like what you're doing, this is very cost effective. I mean, this is just, if you do it well, it's really a shame to not compute these indicators, because even before training, they're available for less than a second. And then once you have computed and select recorded your indicator, you can just train the neural network, wait for 5 minutes, an hour, so yes, depending on the size of it, on your hardware, and then record the final test. So that was like this is the experiment I'm presenting to you, which is very simple. At the beginning, we did much worse. Like we launched the neural network, we recorded all the weights, everything. I had like 20 gigabytes of data on my hard drive for something actually really small and useless, and it was very noisy. So we were like, okay, let's just think about first principles. And the first principle is just doing this. Actually, just look at the final test logs. Okay, so so here's the graph that I'm actually pretty happy with, and that I hope like convinces you, because okay, looks like black magic for now. So I trained so here I have, this is a scatter plot of this FPT quantile, and here like this is the 90th, this is the 90% FPT quantile. So I have this like indicator and the test loss for something like 100. So here you have 100 points. Maybe you have 200. I don't quite remember. It's approximately like 100 neural networks that we train for different architectures sampled a little randomly on a very, with just a standards like MLP with I think 5 or 6 layers on MNIST, just something very simple. And here, so you see this nice correlation here. So you see, okay, so so it tells you this indicator says something, at least statistically. And if you want to compute like a correlation factor, like the Spearman or Pearson correlation, so it tells you, okay, with this indicator, you're at 95. So this indicator that you computed in less than a second is correlated to 95% or to 85% or 83%, so depending on your method of computing the correlation. So 90-ish, and it tells you in 1 second what is the correlation. So it gives you an indicator of your performance after training all of them. So if you have this indicator, you could be like, okay, maybe I should just have trained these. Like, why the hell did I look at these? So, okay, so if you do this, like you could perhaps just by picking it like these, you could have like reduced like your cost of hyperparameter optimization by a factor 10.
A quick question: do you take into account of the training time for
Sorry?
different? Do you consider it's? We are considering the
Yes.
loss that's after training, right?
Yes. So the loss is okay. So the neural select network is just trained following the same procedure with and you stop just at epoch 100. All of them, you just stop them at epoch 100. So all of them have been trained during the same time.
The only difference is initialization.
The only difference is the hyperparameters. So initialization is always different, but the sizes, the architecture is also different. So the initialization, so the hyperparameter search is this. So layer sizes change and gains at initialization change as well. So we could have done non-linearities as well, but like your space just goes bigger and bigger and bigger, and it's like you.
Okay, thank you.
So okay, so that's the idea, and I think like this sort of speaks like in itself. So personally, I have an idea of what is happening, but I have no actual really convincing proof of why like this is going like that way. And but I'm pretty happy about the fact that this experience, you just cannot argue with 90% correlation. There's something there. What is it? What is the exact mechanism? This is a if you're interested, I invite you to think about it, and please tell me. Just okay, so now it's like we're done like with the friendly part, so we move on to the mathematical parts, like that tells you, okay, so like what is this black magic? Actually, Nicolas, thank you very much for suggesting like this word black magic. So yeah, so now it's like this is the time for my own like black magic method for computing this indicator. And okay. So first of all, first basic question. So how do you encode a spectra of large size? Like you have a Jacobian matrix of size. Okay. So I would like to first stress something. So I have this Jacobian matrix of size big N, and N is very large. So this is like the typical size of a layer inside of. So I have a matrix of size 100 times 100. But people who actually do machine learning quite a lot, they know we actually never compute this matrix, because during backpropagation, so this was explained for the first time, like during a very nice talk by Edouard Powers, who actually explained that what actually like the machine does during backpropagation, you only do matrix times vector in order to compute it's like the gradient. So the full Jacobian is never computed. But here we will have a theoretical leverage on it, like this thing that is never computed. So how to encode like the spectra of a matrix J transpose J if it's a very large size? So the answer is very simple. So if you're a statistician, you're like, okay, I have a huge vector of, oh, sorry. So here I'm missing. So this is the spectrum of J transpose J. So it's a very long vector. So the simple way of doing it is just, okay, so why don't I just write plot a histogram of it? And if you say this, just plot a histogram, this means I'm encoding this thing as an empirical probability distribution as this measure. Okay, so this is pretty standard for statistics. If you have a large sample, in this case, they're highly correlated, actually. So you just describe it as a histogram. So this slide is about like definitions and notations. So I'll go slowly on this thing. So you have just to remember like what. So here you have multiple letters, G, M, and S. And they're just different encodings of this same measure. So we saw that a spectral measure, you can encode it to the probability measure. And you have different ways of encoding it, G, M, and S. So the Cauchy-Stieltjes transform is this like integral. So you just integrate this measure against Z minus V on and C plus. This is the upper complex half plane. And it arrives at the negative half plane. So that's the G, and this is called like the Cauchy-Stieltjes transform. And for people that don't know this, so Stieltjes was a Dutch mathematician who finished his life somewhere in Toulouse. And I'm told, yes, that there's a grave of his somewhere in Toulouse, in one of the cemeteries, but never been there so far. And okay, so this is the G Cauchy-Stieltjes transform. This is just a way of re-encoding mu. Then you have this very simple transform which gives you an M. Okay, so G, okay, so that's an integral, that's a bit complicated. Then you have an M, so this is a simple transform. And here's a theorem. So you have to check if this measure is not the Dirac at 0, M will be invertible very high. Okay, so I always make such a drawing. So this is mu. So here you have C plus. This is C minus. I'm not interested in it. And if you go really far in the neighborhood of I infinity, so really far, if you go high enough, so this M becomes slightly invertible. So it's invertible very high in the neighborhood of infinity. And the inverse, the functional inverse as a function is this. And I call this map the S transform like this. 1 plus M divided by M. Okay, so and this thing is analytic in the neighborhood of M equals 0. So warning, very big warning, this is a local object. So this thing I know everywhere where it is defined. This one, actually, there's no answer. It depends on the measure. So this thing is a local object. So it tells me about the inverse of this thing really high. And so I'll just write like this. If ever I have a diagonalizable a matrix, so its spectral measure It's like will be, so I just write SA instead of writing S mu of the matrix. So I'll just skip like the measure parts. So SGM. Okay, so this slide is a little bit not so digest, but at least, you know, you just need to remember the global picture, G, M, and S. And warning, S is a local. I don't really know where it's defined. I have no real control on, so all these things are holomorphic functions, but S, I have no real clue of where it is defined, except on a neighborhood. Okay, so the first landmark, it's like result, like which founded free probability actually. So a landmark result by a very honorable sir called Dan Voiculescu, who's a professor in functional analysis at Berkeley. And so in 1987, so he introduced something called free multiplicative convolution, and in a very like natural way. And he showed that this operation is linearized by the S transform. And actually, here's a very simple way of thinking about it. So the first, so I strongly advise you against reading the paper. Here's a much better way of understanding what he did, but this is, you know, now it has been well explained because he has lots of very, you know, very pedagogical students. So so I pick two matrices, two sequences, such that the spectral measures converge to something. Basically, what I'm saying, okay, pick very large matrices whose profile, whose histogram of eigenvalue look like something. Say this is a Gaussian and this is a Gaussian. What? Okay. And there's a hypothesis here which is technical, which is called asymptotic freeness, and which says that basically the eigenvectors of A and B are completely independent and chaotic. It's like, which is actually what is happening if you initialize everything with independent entries, and you do this product at initialization. So if you do this global Benjou initialization where everything is random and chaotic, this is the, so asymptotic freeness is a technical thing. So this is, okay, under the, so a good way of thinking about it is just saying, okay, so you're just saying eigenvectors are chaotic and they don't talk to each other. They're independent. Then actually, so you have some sort of law of large numbers. So if I look at the product and look at the spectral measure of the product, or the spectral, yes. So look at this thing. Actually, this thing concentrate extremely. Actually, so this theorem is not quantitative, but this converges to some measures, some convolution, because here it's like you're making a product. And this gives you a convolution of two measures that is which is written with this funny box. And this is called the free multiplicative convolution. And it is completely characterized by the fact that the S transforms of A times B is the S transform of A and B. It's multiplied by. So this is funny because then it means that this S acts a bit like a Fourier transform. So let's do it again with just R. So let's assume that here I have two samples, IID. So I have two histograms. So I look at the pairs of sums of eigenvalues. So here I know that the pairs of sum as a histograms will converge to the usual convolution. Okay, and the Fourier transform for sums, for a sum of two, for the additive normal convolution of two measures is the product. So here it is a bit of the same story, but for spectra, except that here the Fourier transform is completely different. And here this convergence actually gives you a measure that is actually funny. So, and if you want to do it, actually, so it's what you do is you pick a histogram, you put it on a diagonal of a matrix. So this is AN. You pick a histogram that you put on a diagonal of a matrix. You conjugate them by Haar independent things. You make the product and diagonalize. and you will see the free convolution. Okay, so this is so I like to present it like this way and not show you any picture, just so that you realize this is a very theoretical object. And in this community, like, they're actually not that interested in numerics and computability. Okay, so that's the first thing. And okay, so first, like, since in our settings, like, we wanted like to do products, so our Jacobian is the product of rectangular like matrices. We need a generalization to the rectangular setting, but this is a small generalization. It's like this is so I don't remember it's like which theorem of, okay, so this thing is done by us. So that if you have large random like matrices which are free, and they have their of size PQ, QR, and such that like all the sizes go to infinity and the ratio goes to C. Then you have some funny, so assuming that everything is asymptotically free, we have in the limit this, so it's not exactly the product, you have this additional constant C here. So actually it's like this requires to actually go really look for what happens in the rectangular setting. So once you have this, so you can define like this operation. So once you have this C, so it's good to treat it as part of the data. So you define some funny operation on measures and scalars C, which is basically some sort of asymptotic ratio of sizes of layers, which is actually, so you say, okay, so here's this operation box, and you say that if you make a product of two large like matrices with relative ratios C1 and C2, then the relative ratio is C1 times C2, and you have some measure nu, and this measure nu is characterized by the S transforms, like where you have to put like the right C here, which has to be C2. Okay, so that's a funny thing, which gives you an operation like which is pretty nice and allows you to describe very effectively this measure. Okay, so allow me to now like just give you the theorem. So if you didn't follow what is this box operation, so that's okay. There's some operation on measures, call it box. It's like whatever. Now, so time for the theorem. So how do we apply this? So you take this J. So this is your long product. Not so long, but the matrices are really big. Okay. So I forgot like to say something. Okay, so I'll make this comment about sizes. So Sichin asked like the question about the sizes, but that's a very good question. I'll get back to it. So we assume that the WS have ID entries, just like Gloraux initializations, just random initialization, and this is like the variant. This is the hyperparameter of the initialization. You have some sort of width profile, meaning that N is large, but the ratio goes to something, okay? And then this is just this is just a notation, and this is a warning if you're actually into free probability, because actually here there's no real freeness, because at the beginning these are independent, but these guys actually slightly depend on the rest. So actually, this is technical. This is pretty horrible. So there's no freeness, but there's a lot of concentration. So building on result of Pasteur and Collins, and these are people in free probability. So here's the theorem. So if I remember well, so this is in our paper, CDK theorem 2.3. So in terms of rectangle, so in terms of this funny box operation, the singular values of Jn converge to this measure, which is the sum. So actually, these are the asymptotic slack measures which are known, and they're called Marchenko-Pasteur. So these measures are actually known. Here you have the relative sizes. And this diagonals like matrices, they're explicit in terms of of the derivative of the non-linearity. So that's the story. Okay, and moreover, the S transform has this funky formula. So then you just have to specialize to different non-linearities and compute it. So, okay, so now, so how do you compute this thing? So, okay, so that's the theorem. So it's like, what do you do? So you fix the width ratios, non-linearities. Then it's like you can form this M guy, and you get this master equation. And actually, we will solve it thanks to some Newton-Raphson scheme, but the story is much more complicated than that. And actually, it's like here I'll specialize to Relu, like non-linearities. So you guys know, I guess this is more for the mathematicians. It's here. So Relu is the function x plus. Hard hyperbolic tangent is this thing. And hard sine is the saw function. So this is this is the fair function of signal processing people. So basically, so here's a formula. Actually, if you pick these non-linearities, I can give you a very closed form formula. I can tell you, oh, okay, the measure is entirely specified by this function, which is 1 over m times a polynomial that contains all the hyperparameters, everything. So this is a simplification, but as you see, this is explicit. Now, so the question is, from this, how do I get the measure? Actually, how do you get the measure, and how do I do it numerically, efficiently, in less than a second? So if you found like the math part hard, that's completely okay, because here you just have to, you just take this master equation as input. And here I'll make a comment about like the question of Sichin. So he asks, okay, n has to be large. Okay, but it's like, what is large? Is it 100? Is it 1,000? So actually, this free probability business, so in free randoms like matrices, things concentrate quite a lot. You have lots of measure concentration, and things are actually like much faster than the law of large number or the CLT. And actually, so the speed of the large deviation principle is n squared. So on log scale, it concentrates at n squared. So if the size of my layers are 500, so like that's okay. You're in the regime. You are in the regime of free probability. So actually, you should not really be scared about, okay, n is large, n goes to infinity. I mean, for n equals 500, this is true. Okay, so now how do I compute this n? So how do I compute this? Sorry, I just need to. Okay, so how do I compute this m? So I need like to invert it, but okay. So this is locally invertible at the neighborhood of 0, but if I go further away, it's not like 1-to-1. So there's no, it's like, what is the, so I actually need to perform analytically some sort of, I need to ask the computer to perform an analytic extension. That's actually like what I have to do. So if you say, so just pick your top of the shelf package and do a search of zeros, like this will be actually very bad. So it's like, what is the strategy? So the strategy is actually, it's like, what do I need to compute? I need to compute this. So remember that there was G, the encoding. So I'll like repeat it. There was G, M, and S. And S was, so this thing is simple. And this thing is expressed in terms of M inverse. So actually, so like what I need to do is here compute this G. And actually, in order to know the measure, you have a very simple theorem by, so it's a lemma, by the Cauchy-Stieltjes formula, which tells you if I look at the imaginary part of this G, very close like to the axis, I actually know the measure. And you have this theorem, weak convergence of measures, like this basically means if you look at the imaginary part very close to the axis, and you look at this thing as a measures, like this will give you the density. So here, sorry, I need to be completely correct. It is not of dx. So, okay, this is absolutely continuous times dx. Lebesgue converges like to this. Okay, so, and that's a picture. So actually here I picked a case where the J, the asymptotic spectral distribution of my neural network was actually the green guy. And I computed G. So here, if you zoom in a little bit, so here, I computed G very close to the axis for this value of Y, then this one, and then this one. And then, so you see, we got close to 10 to the power minus 4. And then it's you see this very nice spectrum of a Jacobian of large size. So this is a nice histogram. And we compare this to a Monte Carlo scheme, and it fits perfectly well. And here's you see for different values. So if you can compute it away, from the axis for this value, so you get this. So you see this lousy approximation. If you get closer to the axis, you get the orange one, then you get this the green one if you get really close. So that's how it's done. So the strategy, if I have to say it very quickly, is because of the Cauchy-Stieltjes inversion. So I have to look at this thing very close to for a very small y. Equivalently, I need let's compute m. M inverse is, oh, so that was theorem 3.3. Sorry. So okay. So the master equations that I showed you give me the M inverse. Then actually I just the only step I need to do is this. And this is actually an inversion of something that is only locally invertible because it's holomorphic. So, okay, so inversion is basically finding a zero. So you're okay, how about a Newton-Raphson scheme? So that should work. And it's so for people that like numerics, so Newton-Raphson, when it works, it's really quick compared to any fixed points method. This is extremely fast. So you're okay, the problem is easy, right? Well, so the warning, this M is known somewhere, and I have to invert it somewhere else and perform some patching and analytic extension in the correct way, because otherwise I won't get the correct values. So is it a bad idea? Well, seemed like a good idea. Now it looks like a bad idea. So it's what do you do? Because we really wanted to save it, because I mean, Newton-Raphson is a very good technique, and its convergence is only local. So here's this is so there's a theorem, there's a criterion by Kantorovich that people in optimization know very well. And it's in 1948. So Kantorovich said, okay, so you look at the Newton-Raphson schemes, what that means. It just actually your computer. So you have this phi z, whose zeros you need to compute in order to have this value. And you just do this phi z of mk, just iterate this very simple transformation. I can compute everything. And maybe this will converge, maybe not. But Kantorovich tells me, okay, it will converge with some criterion. It's you need delta kappa lambda smaller than half, where delta is this, where kappa is this, and where lambda is this, whatever. And then if you check this, then it converges. And convergence is very fast. At every step, you double the precision. You square the error. So using this, we just wrote a function called Isen Bayesian. It just tells me, okay, if I fix z and I look at m fixed, and I ask, so if I start with, so I fix z, and if I start with this Newton-Raphson scheme with this m, will it converge or not? Am I satisfying the Kantorovich criterion or not? And since our m is explicit, this is very easy to do. Okay, so here's our algorithm simplified, and this is where you have the Lilypads. So you saw Newton, where's the Lilypads? So here's the story. So I'm here. I want so here, so I'm very close like to the axis, and I ask, so I'm given Z, and then I'm looking for the appropriate n. So I ask, is it in the basin of attraction of Newton-Raphson? The answer will be systematically no. So I double the imaginary part, and I ask, so is this thing again good? With some guess here, no. And then I just go up, and if I go high enough, actually I have some idea of what the value, approximate value should be, and it should be like 1 over Z prime. So here, so you can prove that for high enough, you are in the basin. So here, it's like you can compute, so you are in some basin of attraction here. So then I can compute like the value for every Z here. And I'm like, okay, now that I have these, so I'll use them as a proxy and start going down. And then again, find another basin here, find another basin, find another basin, find another basin until I get here. And and this is a chaining like method, which sometimes people call it in numerical analysis, just like they call it also an homotopy method. So this is pretty nice. So I guess that this was used like a lot of time by Smale on in complex dynamics. So this idea is a little, let's say, so it's a bit lost in the ages, lost in the literature, but actually it's very nice. I guess like this method actually tells you, okay, Newton-Raphson is your friend. So are there like, I guess, any question? Because so I'm done like with the technical parts, but maybe there are some questions, and soon I'll start like the conclusion and finish just like with the discussion. No.
No. So I guess just, yeah, go your conclusion. Thanks.
Yes. So in conclusion, so here's it's like what we did. So we did a theoretical modeling of the Jacobian, and we used free probability to model the stability of neural networks. And that was a function of the hyperparameters, which are typically widths and initialization variances. But you could add also the non-linearities. You could add other things. So in terms of numerical resolution, it was like we give an efficient and something that is hyperparameter free. There's no tuning. You just ask it, what is the spectrum of that Jacobian? It just spits it out. And there's empirical relevance, and that was actually the part where we chose to do something simple, but at least because it's simple, it's like interpretable. So these indicators, these free probability indicators, so they correlate at 90%. I mean, more or less 90. To the final test law. So this is a tool to choose the best a priori architectures, because you can say, okay, these architectures from this theoretical point of view should not be stable. So you have, so here, like you have a, or at least at initialization, it's like you will have a bad start, or with this one, you'll have a good start. So here, so I'm told it's better to criticize like the work on my own. So first, okay, so there are limitations, of course. And I guess some questions could be, can I do other than feed forward neural networks? Theoretically, yes, but not now. It is possible, but using even more complicated versions of free probability. So if you want to add skip connections, or if you want to stray away from feed forward architectures, the answer, so you won't like the answer, actually. So it's possible, but you won't like the answer. Convolutions. Then, because I know that in imaging, so people ask me, so can you analyze my favorite ResNet, my favorite ImageNet? So can you analyze this? So unfortunately, the answer at the theoretical level is no. The theory is not ready, because convolution operators, they're too structured, and this freeness business doesn't work. But actually, this should not stop the machine learning community from trying to have empirical evidence. Like the theory is not ready, but maybe as empirically that there is something. It just, this is not theoretically justified in my opinion. And I'll conclude with a video a funny like video is that beyond the application to neural like networks, so the method is relevant to free probability and high dimensional statistics. So in order to finish with an amusing video, so this way it's like you get to see free convolution. So what is the spectrum of a large sum of rank 1 projectors? So I just pick some infinite sequence of IAD Gaussian vectors of dimension n. N is very large. The Vn's and Wn's. And the V is the rank 1 projectors that I'm weighting with a factor 3. Why not? Here I'm weighting them with a factor 5. And I look at the and I look at this sum. I look at the spectrum of this sum, and I divide by 1/n. So what happens as t evolves? So free probability tells me, okay, there should be some sort of funny like measure on the line. And how does it move? It's like what is happening? Because so you should think of this as a sequence of convolutions, but here they're additive. This is a sum. So this should be some sort of sequence of convolutions. So this should be some sort of heat kernel moving around. So free probability theory has the answer, but can you show it to me? Okay, so let's show it. So where's the, yes. Okay. So here's the video. So as you see, this looks like a bit like a heat kernel that is diffusing slowly, but actually it's not like the heat kernel, because as you know, the heat kernel has infinite speed, so the support should be infinite. So as soon as the video starts, but it's not infinite clearly, and it looks a little bit like a hydrodynamic flow. So you see like the spectrum sort of moving as this. So these are like the histograms of the spectrum, and you see you have this injection of flow at 3, and so here's, yes, like so, okay, so I think looking at the picture, I made a mistake, because things start at 1 and at 3. So actually, yes, this is a mistake. So it's not like 3 and 5, it's 1 and 3. Okay, but it doesn't change the story. So actually, this is 1 and 3. Okay. I'm done.
Okay, thank you very much, Reda. Sorry, I'm having a coughing attack, but maybe other people have some questions. Okay, I'm not coughing right now, so I'll ask my question. So we use BERT, we use transformers a lot in NLP, and yeah, we don't really understand how to tune them all that well. And so is there really no hope for us with free probabilities?
Well, so let's say that, I mean, so this is basically, so I think perhaps so on this topic, like this is just like the second, maybe third work of its kind using free probability. And it's by far the most numerical one, showing also that it correlates, that it computes things, that it's relevant. So now, yes, like actually, so there's a huge lot of catching up to do, actually. So we need to do other architecture than feed forward. And here, there are things, but you need to catch up. And for convolution, so I think this is not possible theoretically, but you should do something empirical. So I'm not saying it's hopeless. I'm just trying to have a very nuanced point of view in saying, as long as you do fully connected, I have an idea and it should work. And it's not going to be easy though. But if you want to do convolutions, I think the theory is not ready. So if you want to be more flexible with the architectures, as long as you're fully connected, I'm like, yes, there's hope at the level of the theory and the practice and the computation. If you want to do convolutions, then I feel there's no hope at the level of the theory. Maybe you could do something empirical.
And you think that the orders of sort of decrease in fussing around is something like a magnitude of tenfold?
Yes, actually, yeah, okay. So actually this, so it should be of that order, but actually I need like much more sort of experiments to actually be sure of what I'm saying. But I think that everything is in this very nice picture, like which basically tells you, okay, so here's 100 like neural networks. So clearly I should have never tried.
Yeah, those guys. Yeah.
I should have never tried even working like with these guys. So it's like, what did I win? Well, there's approximately 100. So I think here there's approximately like 10 of them. So yeah, it's 10 over 100. So I guess like, it's tenfold. Yes.
And sort of in practice, did we actually, even just blindly looking around, did we end up in that lower right-hand corner, or, have people really been all over the place? I mean.
Oh, so here, this is my own like experiment, but people tried everything. I mean, so here I spent, I don't know, like 2 days of trainings, like to do all the hundreds of them with lots of epochs, like just to be sure that everything has converged. But people have tried like much more, and with much heavier hardware. So
right.
So let's say I'm also interested in trying bigger things. So this is I'm interested in trying bigger things.
Okay, great. Other questions? Oh, there's a question in the Pierre Weiss. Oh, you just said okay. No. Oh, probably to the old comment.
Okay, so there's a raised hand by Noulasser.
Oh, please. I didn't see that. Yep. Jean, is that you?
Is it really raised or not?
It's raised. Or maybe waiting for Jean, I have a very general question. How these results are received by the community? Did you publish them yet? I didn't see.
So it's on the archive since last month. So
okay.
No. So yeah, but hopefully it's like we'll we will submit them soon in 2020. Very early. So yeah, so I just need like to do like more experiments, like bigger things, so that it's like bigger benchmarks. I think like that's the yes, like this is the problem of the work as it is, but that's okay.
Okay.
Yeah. So Jean, we still don't hear you. Okay, Reda. I can't hear Jean Bernard there.
Hello.
Yes. Now we can hear you. Vas-y.
Okay. I have a question about the classical training you mentioned at the beginning, saying that it is very tedious. It can be very tedious at some times because you say you keep initializing, get the result. Are you satisfied or not? Then you try it again. Then in the success stories of DNN, they don't speak too much about this step of reinitializing, trying again and again and again. Can you comment on that a little bit?
So actually, sir, there are smarter, of course, like there's much. So I presented this. So you mean this slide here, but this is a caricature of what people actually do for really big cases. I mean, like this is what I actually do, or it's like a lot of people, I guess, like I think do because it's like this is how things. But actually, so you have but there's this paper of. So this paper, I have to find it, of yes, that was at the very okay. So in this thing, so it's a paper cited by Strobel and al, like which actually details this experiment and says yes, that actually so they initialize like lots of neural networks. But then, so if you have architectures, yes, that work well, so you tend to sort of keep them, remove, so yes, like certain weights, and do something that is more hybrid than just completely independent trials. So of course, you can do something smarter by having some sort of bandit approach. Like whatever works, you tend to do more of.
Okay.
So actually, this is what really people do. But actually, yes. So I chose to follow an approach that is a little orthogonal. Like before even doing anything, can you say something?
Any other questions? I'll look at the participants.
So in the chat, like people are saying thanks and going. So
And leaving. Yeah.
Thank you, Sebastian. Thank you, Edouard. And I think, like, I would like to also, thank Fabrice and Edouard that I've been like talking to, like regarding this, this business. Like they've been very helpful, like in talking, exchanging, and hopefully, this brings new ideas, and you can talk to me later.
Okay. Well, thanks a lot, Reda. Yeah, great. And thanks for the nice talk, and have a great weekend. And we look forward to hearing more about this topic from you.
Thank you.
All right. Take care. Okay. Bye, everybody.